quadratic recurrence relation. So try to look at 5, 1, 2, 3. So title is solutions of some linear recurrence relation. But now we will just say quadratic. Quadratic recurrence relations. Or relations of second order. So, instead of giving you general theory and theorems covering that, I will just start with the example. And then we'll start doing example, and from there we'll make some conclusions and make some plans, and then see variations of that one. So look at this problem. I want to solve the following, to find actually the explicit formula for the recurrent sequence defined recursively 3ak minus 1 plus 10ak minus 2. And let's say also that I want a0 to be 10 and a1 to be 1. So here's the problem. It's 5 units. My first question is this correctly defined recursive sequence? Yes or no? Because I have first two sequences, and whenever I have two previous sequences, I can get the other. So if you want to apply, it's not a big deal. So I start with 10. Next one is 1. What's the next one? 3 times the closer one plus 10 times the one that's further away. So what would it be?
Negative.
I don't know. 103. 103, very good. And then what? 3 times this one plus 10 times the old one. So this would be what? 309 and 10, 319, and so on. Okay? Yes?
That subscript on the A on the second line equals to something equals to
A0. So index is 0 and 1, give you 1 and 10. So I want general formula for this. Can we do that? The answer is yes, and that's what we'll study today. So how does it work? Generally, we say the following. People noticed from experience that solutions very often work for this equation, power function will be a solution. So we are looking at the solution in the form AX equals r to the k, which is exponential function. But we don't know how much is r. And then what do? We plug in this. So this is like a 10. So then I will plug it in and see what's needed. So I get the following. R to the k equals 3 times r to the which power? K minus 1 plus 10 times r to the k minus 2. So if I wanted this to work into B solution, I have to satisfy this. But what happens? I can cancel by r to the k minus 2. And I get the following. R squared equals 3r plus 10. We will not always do this. We'll just immediately write this equation. This is called characteristic equation. This equation is quadratic. When you solve it, it will tell you which r's will work. So which r's will work? You go r squared minus 3r, or solve quadratic however you know. So that will be what? R plus 2 times r minus 5 equals to what? 0. Yes. So there are two solutions. R equals negative 2 and I. So that means, and we'll call that fundamental set of solutions. They are what? So who are my solutions? My first solution is what? And remember your solution was r to the k. guarantee our solutions of this, we call it not differential, we call it a difference equation. So this is difference equation. Okay, so-called fundamental set of solutions. And now what? The general solution of this recurrence relation looks like this. X equals, take first one, multiply by any constant that you want. And take the second one and multiply by any constant that you want. This is called the general solution.
What's the first thing you know?
X equals C1.
Oh, it's a C. Oh, sorry. It looked like a Q.
All right. That was not my intention.
Okay.
So first what? This move is not completely justified. Why? Because that these two are solution, I guarantee, because that's how I chose them, so that it works. So I'm sure that they will satisfy this equation at least. Now, when I combine them, will they also satisfy the equation? That's the story. And the answer is yes. Why? That is the theorem that I will just, I'll ask you for a moment to trust me that this will be a solution, and then I'll go to the theorem and just show you that that's all it is. We call that, now in the language of linear algebra, this is called linear combination of two solutions. Why? You take one of them, multiply by a constant, take the other one, multiply by a constant, and add it up. So this is called linear combination. Of basis solution, or fundamental solution. And they are all satisfy this equation. Now the question is, how much are C1 and C2? As much as you want, whatever you choose. 3 and 7, 3 halves and 9. They will all satisfy the equation. But I'm not asking you only to satisfy this equation. What else am I asking you? To satisfy some initial condition. In that case, there's no ambiguity. I must get to this sequence, don't you agree? And what happens? We call that IDP problem, initial value problem. IDP problem has only one solution. And those initial conditions will actually determine what should be my choice of C1 and C2. So what do? You just plug in k equals 0, or whatever they are. When k equals 0, what should I get? It says here, 10 equals C1 times negative 2, 0 plus C2 times 5, 0. When k is 1, what should I get? 1 equals C1 times negative 2, 1 plus C2 times 5. So what did I get? System of equations in C1, the same way as in the system of equations in C1 and C2, and that will tell you what their choice should be. So how do I solve it? I get 10 equals C1 plus C2, and 1 equals negative 2C1 plus 5C2. Probably the easiest way to solve it is to multiply top 1 by 2 and add them up. What happens if I do that? C1s will cancel. Times 2 and add it down. So I'll get 21. C's cancel. 2C2 and 5C2 is 7C2. So C2 is what? How much is C1 then? 10 is C1 is 7. Here it is. This sequence has the form, let me write it here, that solution of identity problem. It says AK equals, what would it be? C1, which is 7, times negative 2k, plus 3 times 5k. So let me check it, for example, this is A0, A1, A2, A3. Let's see if we did A3 correctly. So A3, or if our formula is correct, well, 531. And I'm not gonna write it on the board, it's just really trivial writing, so I'll just comment on the screen. First, what is it you're telling us, and then how does the proof go? And we'll just look at the screen. Linearity proofs all go the same way. Just the following. Let UN and VN, those are two solutions that already checked, are the sequences satisfying the recurrence relation. Is this recurrence relation exactly of the type that I put on the board, yes or no?
Yeah.
Of second order. Because why is it of second order? Because this difference is L uses two previous members. If it uses only one, that would be difference equation of which order? First order. But since you use two generations ahead of you, that's of the second order. And what else? What's it?
They're both linear. That's linear, right?
Yes, exactly. This is linear, and A and B are the constant. A and B are constants in our case. So what? Then it says, so suppose that the UN and VN are satisfied. Then what? For arbitrary constant C and D, if I do their linear combination, then this will also satisfy the recurrence relation. So how does the proof go? As I said, I don't see the reason why would I write it on the board. Yes, there.
Where, this first part where you said AK is equal to R to the K, where did you get that?
People just they expected it, saw it from practice, they tried it that way. If you remember in DE, the same question.
Yeah.
Why do we guess
I
it's
asked
E to
Howard
the RT?
same thing. He had the same answer.
Yes.
Okay. I was hoping for something different.
No.
Magic.
No, it just, you actually see from those linear ones, because actually there is something there. What is it? Look at this. You say AK equals 3AK minus 1. What is that telling you? The geometric sequence. So this is basically geometric sequence tweaked a little bit. And that's what people say, let me try geometric sequence. And then two geometric, so that means if no one's interacting, one geometric sequence will work. And the other, so they try geometric sequence because is this how geometric sequence looks like? So it's very reasonable attempt.
So we use R to the K with a situation that looks like the AK minus 1 and AK minus 2.
Exactly, yeah.
And then if it's just AK minus 1, we don't use it, right? Or we do?
No, you use it even more.
Okay.
Oh, that's immediately. If it's AK minus 1, it's just geometric.
Okay.
That's what we
It's
did
just
last time.
geometric. Now it's, what about minus 3?
What's it?
What if you went to AK minus 2, another term?
They have the same thing. Now you will get cubic equation and you get three solutions the same way as in D.
Okay.
But what I don't hear you asking is the following. What if I have here
Non-linear.
plus, 3 or plus 3k or something like that? What happens? Those are called non-homogeneous equations. If you remember these, if this is clean, only the previous members, that's called homogeneous system. What if it's not clean? If there is something else like n or number or something that's called non-homogeneous system. And that one I just touched a little bit. I don't know if I have time. That's in the beginning of section. I wanted to give you one homogeneous, although I might explain it a little easier than what I did here. So if I have time, I'll discuss it. If not, on Monday. Anyway, so what happens? Why is linear combination of solution? So here it is on the screen. Can someone comment? What did I do? I took my, so who is this? Is this my new solution that I'm trying to show the solution? Yes or no? So I'm trying to show that that one also satisfies the same recurrence relation. So what do? CUN plus DVN. Is the UN assumed to be solution already? Yes or no? So for UN, recursive relation is true, so I replaced it. For VN, I did the same. That's recursive assumption. And then what happens? It's not recursive, it's just assumption on U and V. And then what's my only goal? To rearrange them. So look at this guy and this guy. Do they both have A, yes or no?
Yes.
I factored it out. Who appears? CUN minus 1 plus DVN minus 1. For these two, I factor B times what? CUN minus 2 plus DVN minus 2. Does this look familiar? Who is this? Is this the same guy, just W on the previous level? So this is WN minus 1, this is WN minus 2. When you check it, I should have written here that this is Wn, because that's what Wn is on the previous line. So it says Wn satisfies the equation. So it's very simple, just plug it in and use linearity. All right, what else? So we talked about this. Here's the story. Here's what you just asked me. Fibonacci sequence. So can we write, can we find explicit formula for the Fibonacci sequence? The answer is yes. So what is the formula? It won't look nice. But actually whatever we discussed last time about that convergence and so on could be seen from that formula. So here it is, 550. We have what? N equals n minus 1 plus n minus 3. So now I'm not going to do r to the n because I did it first time, so if you see what's going on, I just immediately write quadratic equation. That's characteristic equation. So what is the equation? R squared equals what? R plus 1. So those coefficients here are your coefficients of quadratic equation. Look at this. So here, if you look at this and that quadratic equation, look at this and this. Can you read this quadratic directly from here? Yes or no? Yes. Use your coefficients of recurrence as coefficients of the quadratic equation. And by the way, don't forget, your solution is r to the n. Or r to the n. So what then? I get quadratic equation, I want to solve it. R squared minus r minus 1 equals 0. And who appears? R equals what? 1 plus or minus square root of 5. Here's your golden ratio. So what then? I know that my solution is what? First one will be 1 plus root 5 over 2 n. The other one would be 1 minus root 5 over n. And then I just mix them up however I want. Here's the general solution of Fibonacci relation.
Now do that matches like 1 and 1 or
Exactly, exactly. So now what happens? But you want not any solution. You want the one where A, we should call A0 is 1. And A1 is 1. Okay? And then what? These numbers are very unpleasant to write. Very. So I'll call them alpha and beta. It's easier to write alpha than write all this quotient. So when I plug in the initial conditions, I get the following. So 1 equals C1 alpha equals 0 plus C2 beta. And 1 again is C1 alpha to the 1 plus C2 beta to the 1. Do you agree with me? So now I need to solve this system. Oh, I would love to use Kramer's rule here. Does anyone know Kramer's rule? Those from these know, and I don't know the others.
Oh, yeah.
Yeah, so Kramer's rule would say the following. You can solve it however you want. You can look at my notes, elimination and everything. But Kramer's rule says the following. Make a determinant of the, who are my variable here? C1 and C1 and C2. So determinant of this system is what? Alpha or 1, 1? Alpha, beta. So that would be what? Beta minus alpha. So you put determinant of coefficients. Then you do alpha determinant. How do you get alpha determinant? In the basic determinant, that you replace column of alphas with the right side. So it will be 1, 1, 1, beta. So this beta minus 1. The same way d beta is what? 1 alpha, 1, 1. So what would that be? 1 minus alpha. And then what are my solutions? Solution says alpha equals d alpha over d
C1 and
is
C2?
1 minus root 5 over 2. If I subtract them, what do I get? Beta minus alpha is just minus root 5. Because 1 and 1 cancel.
Yeah.
Root 5 gets 2 negatives over 2, you get negative root 5. So alpha equals beta minus 1. Beta minus 1 gets negative. This 1 half minus 1 is negative 1 half. So we're going to negative 1 minus root 5 over 2 over negative 5. And how much would that be? Minus here, this will make it plus. So it's a 1 plus root 5 over 2. Oh, no, those are alpha and beta. Sorry. Who are these? Where are my variables?
C1, C2.
I have to correct. This is D1 and D2. And these are C1 and C2. Sorry. This is C1. And now here is C2. So what? The beta minus alpha is the same, which is minus root 5. And the 1 minus alpha is negative 1 minus root 5. So 1 minus alpha is negative 1 minus root 5 over negative 5, which would be a little more careful in negative 1, beta minus 1, beta minus alpha is okay, beta minus 1, negative 1 minus, yes. And on the bottom I got 1 minus alpha is correct, yes. So it should be what? 1 plus. By the way, are 1 minus alpha and beta minus 1 the same thing? Beta minus 1. So what would that be? Looks like, no, this is minus 1 minus root 5 over 2. So it looks like 1 plus root 5 over 2 root 5. That's correct. Let me check. And that's something minus. One of them should be, I should have a minus on this one.
Yeah, you should have a minus on
That's how
the
I
top
do it.
one there. On C2, sorry.
Oh,
C2 should be 1 minus rad 5. Because you have 1 minus alpha, and alpha is 1 plus root 5 over 2. So for C2, the numerator should be 1 minus rad 5 over 2.
all right. I like it, so I'll accept it. So here it is. So it should be negative. Oh yes, that's 1. No, it might look like 1 minus alpha. Or beta minus alpha. Whatever. This is very bunch of look. So what do we have? It's interesting that what? C1 has 1 plus root 5 anyway over 2, so we can write it like this, 1 plus root 5 over 2 to the n plus 1, because there is another 1 plus root 5 over 2, the only extra is 1 over root 5. And then plus 1 over root 5, 1 minus root 5 over 2 to the n plus 1, because this constant, C2, 1 minus root 5 over 2, joins this power, beta to the n, so that part joins to the n plus 1, there is only 1 over root 5. And, maybe it's minus. Yes, it 8 minus, just check my classes and minus. So here it is. So what is that basically telling you? What it tells you is the following. It's interesting how Fibonacci sequence behaves. So look how complicated the expression looks like. And on the other hand, we are just getting nice numbers. So these numbers are like 1, 1, 2, 3, 5, 8, 13, 21, so on, using those square roots of 5. So what happens basically? Where are those square roots of 5 disappearing? They are disappearing just like if you remember how the complex numbers sometimes, when they conjugate complex numbers, how i's and i's cancel? The same thing happens here. And there's one more thing. Those two factors have completely different influence on our number. Why? Because look at this number here. What is the base of this exponential function? 1 plus root 5. Root 5 is 2 point something. 3.2 over 2, 1.6. So this is bigger than 1. So this is exponential function. Agree? This is where actually the Fibonacci sequence is exponentially growing. What about this guy? This guy is tiny. Why? Because look at this. 1 minus root 5. This is like negative 1.2 over 2. This is like negative 1/2. So what is this doing? When you raise it to high powers, the decrease is approaching 0. But what is it doing? Since it's negative, it does alternation. You remember before it goes up and down, and actually, so this guy is really doing just little changes, go above or below. This is really where you get Fibonacci sequence. So if you plug in n into this member, you will see decimal that's very close to the Fibonacci, and then just round it and you will get the Fibonacci. But you don't know. Sometimes you round it up, sometimes you round it down, depends on these guys. But generally, this second guy is very, very small. But anyway, just you have a formula for the Fibonacci sequence, and then you don't have to calculate that. There was a comment or a question.
I was just thinking, based on your answer over there and the comment that you just made, shouldn't that be a plus between them then, because the alternation is being done through the 1 minus root 5?
So here it is. No, that doesn't matter. Alternation is done through this.
Yeah.
So alternate one way or the other to decide what it is. Instead of going through my pluses and minuses, just check it when n equals 0. And that's what I did quickly when I solved the result. So here it is. You get what? Full out 1 over root 5. And then when n is 0, what do you get? 1 plus root 5 over 2. And then should I have plus or minus 1 minus root 5? If I have plus, they will cancel, and I'll get 1 over root 5, which is wrong. But if I have minus, then 1's cancel. I get 2 root 5 over 2 root 5 cancel. I get 1. So generally, it is minus for sure. And then, as I said, where did I lose that minus? Somewhere in the R, plus and minus. But generally, it's all later. Yes.
So just, if we did want to get rid of that minus, could we make it a plus and then change the power to n?
I would rather keep this as a nice symmetry here, so that's no better, but you can do algebraic or whatever. Okay? Then what? So Fibonacci really could be written in this form, and here. What happens here? Sometimes your quadratic equation might have single root. So what would that be? Which is the same thing we had this in differential equations. And let me give you the example, and I'll discuss it more. The example 534. So multiple roots. We have the same thing in DE. Is what would that be? Here's the equation. Cn equals 6Cn minus 1 minus 9. It should be C. There's a whispering there. It's not B, of course. It's C there. Cn minus 2. calculation, and we can actually do the calculation. What would that be? How much is C2? 6 times 21 minus 9 times 2, and that would be what? 126 minus 18, 108. And then you keep going, and numbers are uniquely determined. Let's see, how do we calculate them? So, we make characteristic equation. Characteristic equation would be r squared equals 6r minus 9. And then what? Now we solve quadratic, r squared minus 6r plus 9 equals 0. But what happens here?
R minus 3.
This is a perfect square. This equation has only one solution. Doesn't it? So did we get a solution?
Yeah.
Yes, we did. So here's your fundamental set. Is 3 to the k, or 3 to the n.
Isn't that a repeated solution though?
It is, yes, a double solution. And then what? So 3 to the n is solution. If I plug it in, it will work. But I'm unhappy about it because I need 2 of them. Because 2 of them will generate and give me everything. So the question is, where do I get the other one? So it's entry.
That's right.
Yeah.
Multiply by n.
Yeah.
That was always the easier to rule
That's
more.
the
Yeah.
same thing from the yes. So why is that working? So why is n times 3 to the n also a solution? I'll answer it in a second. Here, I'll show you the theorem, but let me finish the problem. So how do we finish the problem then? If we are kind of saying, okay, if it is solution, we are not convinced yet, but we'll come back to that. Then we finish it what? We say Cn equals C1 times 3 to the n plus C2n times 3 to the n. Which even makes it nicer. Can I factor out 3 to the n now? Yes or no? 3 to the n times C1 plus C2n. And now I match initial conditions the same way. So C0, which is 2, equals 3 to the 0, which is 1. So we get C1. Because C2 times 0 is 0, which is even nicer. Then second one disappears. And then C1 is what? 21 equals 3 to the 1 times C1 plus 7 is equal to yes, 7 equals to C1 plus C2. We already have C1 is 2, so C2 is what? 5. So solution is the one that we want. Cn is
2 times
3 to the n
times 2
times 2 plus 5. So for example, for n equals 2, that would be 9 times 12, which is 108. So the only question is here, why is this also a solution? So why is that in general case? So here is the theorem. Okay, right? No, I did it. I just showed it us. So what is the proof that this n times 3 to the n will also be a solution? Let me erase this part and have this next. So what? If I have recursive relation, and if it says that Cn equals a Cn minus 1 plus b Cn minus 5. Is that how it looks? So this is the form of this equation. Instead of showing it for 6 and negative 9, we'll show it in a general case. So what? Case when characteristic equation has double solution. look, actually it will look like this. When I complete the square, what do I get? R minus what?
Would that be minus B?
Minus B. So what would that be? Either or what? If equation has double solution, it is discriminant equal to 0, yes or no?
A over 2, right?
So, yes, so either complete the square, so it would be what? R minus A over 2 squared will look like this.
B over 2, right?
A over, no. And then what? Of course, all right, let me do it in more details. R squared minus AR, and A squared over 4, I will subtract A squared over 4 minus then this is R minus A over 2 squared. And then what? Then this has to be 0. So generally it says that this happens B equals that's the price of that. So then, if this is the case, then equation looks like this: R squared equals R minus A squared. This is characteristic equation. And then the original equation looks like this. The original equation looks like what? Cn equals A times Cn minus 1 and minus A squared over 4 Cn minus 2. So that will make it complete square. And then I want to show, so what would that be? What is the who is the solution of the characteristic equation? R equals what? No, if you complete the square, what's the solution? R equals what?
A over 2.
Solution is R equals A over 2, and we know that if I have AN equals what? A half to the n, then that checks. That's what we know from before. If I plug it in, you will see that easily. But I want to show that who also up here works n times A half to the n. And I don't know that yet. What should I do? Check it. Plug it in as yes.
In the beginning, don't you want this to be minus B, Cn minus 2 sort of deal, so that you end up with, at the very start, Cn equals A, Cn minus 1 minus? Isn't that what you want? You want minus there?
Wait,
Because if you have the minus B, R squared minus AR minus B, that doesn't make sense to me to be able to get a perfect square. It doesn't need to be plus B. Never mind. It doesn't matter.
no, B is negative, so however you call it. It's B negative.
Okay.
If you want kind of
I
know that
understand.
in
I
advance,
understand.
that's fine.
Yeah.
It's up to you. That's an option. I'm not saying it's wrong, but I don't see big reason for it. So here it is. Let's check it. So left side looks like this. So Cn equals n times I have to n. What about the right side? Looks like this. A times Cn minus 1 minus A squared over 4 Cn minus 2. How much is that? A times. How much is Cn minus 1? There will be a little algebra here. How much is Cn minus 1 from here? N minus 1 times what?
A over 2 raised to the n minus 1.
Minus A squared over 4 times what? How much is Cn minus 2 then? N minus 2 A half.
You plugged in the value that you wanted to test back to the top
Exactly.
in the first one?
Yeah,
Okay.
exactly. And here it is. So here's my equation that I recognize how much B must be if you want to have multiple solutions. And then from there, I calculated my left side. Now I plugged into right side, and I should show that these two are equal. If I show it, it works. If I don't show it, first one?
N minus one.
It's n minus 1 times 1/2 to the n minus 1. Because I put a, but not half. Minus 1/4 n minus 2, 1/2 n minus 2. So my an's are good, but I left halves for a moment. But what would that do?
Can you take a half out of the 1/4 and put it into the half on the right?
So this 4 is 2 squared, really. Is that like 1/2 squared? 1/2 squared, then 1/2 to the n minus 2, that's 1/2 to the n. So I get n minus 2, 1/2 to the n. Unfortunately, this guy doesn't have 1/2. What do? Make it artificial. Multiply by 2 and divide by 2. You understand the move?
Shoot it up.
I multiply by 2, I multiply by 1/2, that half is back. So what do we get now? Pull out 1/2 to the n with a to the n, so we get a half to the n. Who's left? 2n minus 2 minus n plus 2 plus n minus 2, 2n minus n is n. Voila. So it's n times a half. Look at this, once you check it, you trust it, and then from now on, we know that if one of them works, there is a shorter solution, shorter explanation for this bloody language. But of course, you have to assume special value on a b if you want. Yeah. That's it. So today, what did we learn? Quadratic equations, and then that are homogeneous, and that have real solutions, or a real solution, not imaginary solution. We don't discuss those. So real solutions, repeated or not repeated. Is that clear? Now, quick discussion of that one problem that I did in the beginning of the section, because I was going to show it in different. In the beginning of the section, I didn't do second order, I did the first order. And I did it in quite a complicated way, because I really didn't want to rely on these at all. So I did that, like, you know. So I wanted to discuss something like this. So this is basically non-homogeneous. So just quick discussion of non-homogeneous. Non-homogeneous different equations. And this one is even simpler. It's a linear. So it looks like this. Okay, and equals 2an minus 1 plus n. And a is a0 equals 3. Okay? And as I said, if you look at my notes, there's a page and a half of calculation on this. There are some interesting recurrence relations. It's interesting, but there is a much simpler solution if we apply the ideas from differential equations that work here as well. So what do we do? Is this non-homogeneous part, yes or no? So let's do homogeneous part first. Homogeneous. So what would that be? an equals what? 2an minus 1. Did you see that? This is very easy. I don't need any recurrence or anything. What is this? Is it geometric? So what is this telling you? This is the equation an equals 2 to the n. Does this one satisfied? But what is my problem? I need somehow to, yes.
Does that satisfy the initial condition?
No, forget the initial condition. That comes at the end. So, so what is it? My solution looks like this. an equals 2 to the n, but that's for homogeneous. What about non-homogeneous? Then what? I'll just guess a solution, and I'll say the following. some solution Bn in the form of a linear function An or Kx plus L. If I'm lucky, Kn plus L, sorry, I'm too much in these. Kn plus L. So linear function of n, if I'm lucky, I might find it. If I'm not lucky, nothing else. We'll try something else. So what happens? Let me plug it into the equation, An. Or better call it Bn, because this one is called An. Bn. So that's my lucky attempt, and I'll plug it in. And it says the following. Kn plus L equals 2 times An minus 1, which is what? Bn minus 1, which is what? K times n minus 1 plus L and plus n. Do you really mean? So when I plugged it in, I said, I don't want to make up my mind what K and L are. I'll decide later on whatever might work. So I plugged it in, so what do I get? I get the following. Kn plus L equals what? When you distribute, you get the following. 2Kn minus 2K plus 2L plus N. So from here I get Kn plus L equals combined n's, which is 2K plus 1 n. And plus 2L minus 2K. You ready? And now what? If I want this to happen, this must be equal to this. So what do I get? Do I get equation in K? This is called UC method, or method of undetermined coefficients. K must be 2K plus 1. So how much is K? How much is K from here?
Negative.
Negative K is 1. K must be 1. Okay, if K is negative 1, then these two things will cancel. I also need to match these two guys. It says L equals 2L minus 2K. Get K is left, L on the right, we get 2K equals L. So how much is L? Was I lucky to find the solution? So what would that be? My Bn is solution of homogeneous equation. It looks like what? Negative K minus 2. But that's only one solution. I want all the solutions. What? Yes, negative answer. And then what? How do I get the general solution? It says the following, like in these. Take this as a generator and take this as a shift. So solution is this. An equals C1 times 2 to the n minus n minus 2. So this one, if you plug it in, it will always work. Because this guy will satisfy this part of the equation, this guy will satisfy this part of the equation, everything will match. And then what, as you asked me? But so you assemble first homogeneous part, you are guessing non-homogeneous part using so-called UC method. When you get them together, here's your solution. What's missing?
Initial value.
Initial value, but then what happens? When I plug in 0, I get 3 equals C1 minus 2. So how much is C1? The solution is An equals 5 times 3 minus n minus 2. Let me see if I got the same solution. Is that a solution that you have there? 5 times 2 to the n minus n minus 2. The same solution. And this is much less work. But what? Here are a couple of details missing. It's not justify why it's all this correct. I'm just relying on what you might know from differential equations. So or just memorize the procedure. It's much easier than what I wrote in my book. All right. One more reminder. If this is the end of the chapter, that means what? Homework due on Monday.